Is it possible that the key to unlocking true artificial intelligence isn't about building bigger models, but about understanding them more deeply? Welcome to a special edition of the Intelligence Revolution. Today, we are diving into a groundbreaking collection of research that suggests we are standing on the precipice of a new era in AI. Instead of just chasing raw computational power, scientists are now focusing on clarity, structure, and the very nature of how machines think. You will learn why simple approaches are suddenly outperforming complex ones, how our digital agents are learning to express uncertainty just like humans, and why the mathematical foundations of our neural networks needed a crucial correction. Stay until the end, because the final insight about the geometry of deep learning will completely change how you view the technology shaping our future. For years, the dominant narrative in artificial intelligence has been a race toward scale. The assumption was that if we could just feed more data into larger models, the problems of reasoning, error, and understanding would solve themselves. We poured resources into massive systems, believing that complexity was the only path forward. But this approach created a paradox. As models grew more powerful, they also became more opaque, prone to subtle errors, and disconnected from the fundamental structures of logic and language. We found ourselves with black boxes that could predict outcomes, but couldn't explain why, systems that hallucinated details, and frameworks that struggled to align numerical confidence with linguistic expression. The field was hitting a ceiling, not because the technology wasn't advancing, but because we were ignoring the foundational cracks in the architecture. However, a wave of new research is turning the tide. Imagine a scenario where a simple, direct question yields a better answer than a complex, multi-layered analysis. This is no longer hypothetical. New evaluations, such the Q-Val framework, have demonstrated that simple, direct prompting baselines consistently outperform complex, dense supervision methods across dozens of techniques. It turns out that by stripping away unnecessary complexity, we allow the signal to shine through more clearly. But the breakthroughs go even deeper. Consider the challenge of uncertainty. For a long time, AI systems struggled to admit what they didn't know. Now, through reinforcement learning with metacognitive feedback, researchers have achieved a 96% win rate in human evaluations. How? By aligning the machine-expressed uncertainty with its intrinsic belief. It is as if the AI has learned to hesitate before speaking, to use linguistic hedges that match its internal confidence levels, creating a harmony between number and word that was previously missing. Perhaps most startling is a discovery in the very mathematics that underpins these transformers. For years, we treated the arrangement of data coordinates as a simple permutation game, but new work on the signed permutation gauge reveals that this was a fundamental mismatch. Transformers based on RMS norm actually require a signed permutation structure to preserve coordinate identity. It is akin to realizing that a map of a city is useless if north is constantly shifting. By fixing this structural gauge, we ensure that the optimizer states and steering vectors remain consistent, no matter how the model rotates or transforms. Furthermore, we are seeing AI correct its own careless mistakes. By utilizing critic models to detect data referencing errors, researchers have improved final answer accuracy by nearly 12%. This proves that many errors we thought were inevitable flaws are actually correctable issues. Whether it is decomposing uncertainty into context and multiplicity, or transforming implicit reasoning traces into explicit, executable plans, the common thread is a move toward precision. We are moving from vague approximations to faithful calibrations, ensuring that when an AI reads a table or analyzes a text, it does so with a level of care that mirrors human scrutiny. So, what does this mean for us, for science, and for the future of humanity? These findings signify a profound maturation of the field. We are witnessing a decisive shift from the blunt instrument of general-purpose learning toward domain-specific instruction and structural intervention. This is not just about making computers faster. It is about making them trustworthy. When AI can faithfully calibrate its uncertainty, it becomes a safer partner in high-stakes environments like medicine, where reducing reasoning failures from 64% to 13% can literally save lives. When we correct the topological constraints of our networks, we unlock new levels of efficiency, allowing models to achieve over 80% of a teacher model performance at a fraction of the size. This democratizes access to high-level intelligence, breaking down barriers of cost and complexity. Moreover, by distinguishing between superficial agreement and deep alignment, we challenge the assumption that mechanistic findings automatically transfer across models. This fosters a more rigorous scientific culture, where we value understanding over mere prediction. Ultimately, this movement suggests that the next revolution in AI will not be defined by the sheer scale of our data, but by the elegance of our understanding. We are building machines that do not just compute, but comprehend. Today, we explored how simplicity is defeating complexity, how uncertainty is being humanized, and how structural corrections are solidifying the foundation of our digital minds. These insights remind us that in the quest for intelligence, clarity is the most powerful tool we possess. If you enjoyed this journey into the heart of AI research, please like this video and subscribe to our channel for more deep dives into the science that shapes our world. I want to hear